First is an integrated micro traffic flow model. Okay, so in the traffic flow model, we have three basic variables: flow, density, and speed. We know flow is the number of vehicles moving past a fixed point on a roadway over a given time period, and density is the concentration of vehicles on a particular section of road at a specific point in time. And also we have time headway is a time period. Time headway, for example, one vehicle passing through this point and calculate the time for the next vehicle passing through the same point. This is time headway and distance headway. So for the picture, this point from this is the distance headway. Okay, based on these definitions, we have some relation for the macro model to micro model. Okay, for the flow, it should be 1 over the average time headway. And for the density, it's 1 over the distance headway. So we have connections for the macro model and micro model. Of course, for S3, we just talked about it has macro model, it has micro model. And also for the IDM, intelligent driver model, it also has its macro model and micro model, and the same for OVM. Okay, there are some inconsistency between the macro model and micro model. This is the research motivation of this study. There are some inconsistencies. First, theory inconsistency. So the requirement for Q equals K times V is the steady state traffic flow. So the second inconsistency, we call it model inconsistency. For example, in the macro model, you use green shows, and for the micro model, you use IDM. They are not consistent. And also for the data inconsistency, we usually use detector data. For macro model, we usually use vehicle trajectory data. For the micro model, they are data inconsistency. And also the results inconsistency. Here, look at this one. If we collected some speed density data and we calibrate based on this speed density data, we will obtain this curve, the blue one. But if we calibrate the vehicle trajectory data, calibrate the micro model, and substitute the micro model parameters to the macro model, we will obtain this one. They are not consistent. We call this result inconsistent. So based on this motivation, how to overcome this inconsistency? So for the theory inconsistency, we need to extract the steady state rather than all the data set for the macro fundamental diagram. We will use a machine learning approach to extract the steady state traffic flow data. And for the model inconsistent, of course, we should use the consistent model. For the data inconsistent, we should use the same high resolution vehicle trajectory data. We can extract the small cells, for example, 50 meters in space, 30 seconds in the time, and use these cells to calculate the speed density flow data. And results in consistent, we should propose an integrated macro and micro traffic flow model calibration. Okay, we have designed this framework. It has 3 modules for the macro fundamental diagram model, for the California model, and for the macro-micro integrated optimization. So for the first part, we need to prepare macro fundamental diagram modeling. How can we do this? We can divide the space-time trajectory into very small cells, not so large, very small cells. In this study, we use 50 meters in space, 30 seconds in time. Okay, we can add this definition to calculate speed, the flow, density, and speed. Okay, so how can we extract the steady state? We just divide the whole space-time trajectory into very small cells, and for all the small cells, we use different deep learning algorithms. In this case, we use 3 blocks: RAS network, efficient network, and transformer. And use these different blocks. This can be used for feature extraction. So we will extract the feature from these small cells and use an encoder, decoder, and then use softmax for classification. The result is we can obtain whether this cell is in non-steady state or in steady state. This is the output. So this is a classification problem. Okay, for module 2, it's related to micro-Carforian model. For the micro-Carforian model, we need to determine the Carforian pairs, different Carforian pairs. And when we select the Carforian pairs, we need to set some rules. For example, the following time shouldn't exceed T minimum and with no length changing. This ensures it is in a Carforian state. And the maximum spacing between leading and following vehicle should be less than Smax. So if they are very long, the distance between these 2 vehicles are very long, so it's not in a Carforian. And rule 3, the following period should include at least 1 acceleration and deceleration, because in the Carforian model, it should be used to capture the traffic dynamics rather than all in a free flow speed. And for the calibration, we can choose the measure of performance, MOP, using the position and using the speed. And these are very simple derivations. The basic idea is based on the Newton's moving law. Okay, now we will have the integrated optimization framework. We have 3 objective functions. F1 is for the macro model. F2 and F3, they are for the micro-Carforian model. And psi is the feasible region for all parameters, theta. Theta is a joint union of macro parameters and micro parameters, because in the analysis we have some physical meanings, physical connections between macro model and micro model's parameters. Okay, this is the multi-objective optimization. So we propose an improved multi-objective Y-shaped optimizer approach. We call it improved because we set some new properties. For example, the good point set, the additional update for the worst solution. We add some rules to improve the original model, and we will compare the results between the MOWSO and IMOWSO. Okay, this is a good point. Good point set. On the left-hand side, this one, it can generate a uniform initial population. We call this a good point set. But for the random, this one is not a good point set. If we incorporate the good point set into the calculation, the results will be much better. Okay, this is the general framework of the IMOWSO. So why I choose IMOWSO? This is because in the MOWSO, it has a lot of benchmarks. So we can compare the performance of our proposed methods with the benchmarks. And it also integrates some baseline algorithms. We can compare our algorithms with other algorithms. And we use different evaluation indicators. For example, we use IGD, average computational time, ACT, and hypervolume. These three performance indicators. Okay, here I just show you the results. Okay, we compare the original app, the MOPSW partial swarm optimization, NSGA2. These are the three baseline algorithms. We compare our results with these baseline algorithms, and this one is without this MOWSO is without improving structure, and this IMOWSO star this without the good set point. And this one is our proposed algorithm. We can see in almost all the cases, our proposed algorithm outperforms the other algorithms. Okay, both in terms of the best case, worst case, and also average computational time. Okay, we also compare our proposed method. Here is the hypervolume value, and this one is IGD and average computational time. Okay, if we look at the hypervolume, it's also our proposed algorithm outperforms others. The next one, no, not the next one. We also did some empirical analysis for the macro-micro traffic flow modeling. We also use the ZTD. As I said, this data set is very good for micro trajectory analysis. Okay. If we look at this illustration figure, we have 5 different states. We have 5 different states. We can see in this state, we can see the speed are the same. They maintain a relative stable speed, so it's in a steady state. But in state 2, the speed changed, right? The speed changed. This is a shock wave, and you can see the speed changed. So in state 2, it's non-steady state. And state 3 is steady state, state 4, non-steady state, state 5 is steady state. If we look at the trajectories, we can see, for example, in this state, it's non-steady state, non-steady state, non-steady state. But for the lower, these are in steady state. And if we look at the speed density, we can see the blue one is non-steady state, and the red one is the steady state points. Okay, we can identify. So here we use the confusion matrix to compare the results. We can see this one, if we only use REST network for the steady state extraction, we can see the results for the true negative and for the true positive. The performance is not quite so good. And if we look at the efficient network and also transformer, the performance may be good in true positive, but not very good for the true negative. But if we look at our proposed method, both the true positive and true negative, they are very high and much better than the other 3 models. This is very interesting. Here, if we if we look at this figure, the red one is the observed spacing of the following vehicle, and the blue one is the estimated spacing of the follower. Okay, now you can see if we directly calibrate using the this blue curve, they are almost the same, they're very close. But if we first calibrate the macro model and then submit the macro parameters into micro model, we will obtain these results. They're quite different. And similarly, if we look at this curve, if we directly calibrate the macro model, we will obtain very good results. But if we calibrate the micro model first and submit the good performance in the micro model into the macro model, we will obtain this curve. The result will be much worse. Oh, sorry. Okay, because in this analysis, we don't have the ground truth parameters. We don't have the ground truth parameters in this analysis, so we cannot evaluate the performance. So in the next experiment, we use simulation, because when we use simulation, we need to set the parameters first. So this will be treated as the ground truth. Then we calibrate, we run this simulation. It's on a circle road with only one lane, and the spacing between each vehicle in the beginning is 20 meters, and they run, and we add some disturbance. For example, one vehicle decelerate and then accelerate. Okay, so we treat this, and then we can obtain the steady state traffic data. If we look at the confusion matrix, we can see because in this case we have the ground truth data, so we can compare the simulation, the analysis results with the ground truth. And we can see the true positive, true negative, they're all one, very perfect results. And also, we can obtain the steady state and non-steady state. We can, because in the simulation, we can set different simulation time from 0.01 to 1 second. And in traffic flow analysis, we usually use 0.1 for the analysis, and we can see almost the errors, because in this case we have ground truth, so we can evaluate the errors. Okay, we can see with our proposed integrated optimization algorithm, the errors are almost below 10%. Okay, as I said in the S3 model, I didn't introduce the S3 K-following model because I said there's some problems, there's some errors in the S3 K-following model. So I did another work, we call it extended S3 traffic model to solve the problems in the original S3 model. I will introduce what's the problem in the S3 model. Here, this is the original S3 traffic model. It's macro model and micro model. Okay, if we look at the micro model, we can see the acceleration for the vehicle, for the following vehicle is related to delta x, delta n. This is the space headway. This is the speed difference. So once these two are determined, we can calculate the acceleration. Okay, now think about this case. When delta v is 0, which means the speed difference is 0. Two vehicles keep the same speed running on the road. In this case, because delta v is 0, So the acceleration will be always 0, no matter how close or how far they are. This is not a real truth. So when the speed difference is 0 between two consecutive vehicles, the acceleration of the following vehicle would always be 0, no matter how close they are. And this will cause collisions during traffic simulations. So for the ES3 model, we need to overcome this property. How can we overcome it? It's quite, we propose a very easy approach. We just add a desired space headway. We add a desired space headway here. So this is the observation, the real space headway, and this is a desired value. Then when the speed difference between two vehicles is 0, so the delta V is 0, then the first term will be 0. We just focus on the second term. If the space headway, this one, is large than the stationary space headway, so this will be positive, and lambda is positive, so acceleration will be positive. So the foreign vehicle will accelerate to reach to close to the front vehicle. Okay, with some very, so the H star is the stationary space headway or desired space headway. We can derive this desired space headway with some derivations, and finally, we will obtain our new ES3 Cavorian model. It's in this form. Actually, we just add a desired space headway term in the second term. Okay, and this paper is in major revision in KRC, and we still try to revise it. Okay, we did a lot of experiments. In this experiment, the scenario is easy. We have 20 identical vehicles travel on a single lane, infinitely long road, and no lane changing. And the initial state is that all vehicles maintain the same initial speed, and after reaching an equilibrium, a perturbation is applied to the leading vehicle, and the leading vehicle decelerates at next 1 meters per second square for 3 seconds, and then accelerates at 1 meter per second squared for another 3 seconds. And the objective for this simulation is to analyze how the disturbance propagates and affect the entire traffic flow. So we can compare the original S3 model and the extended S3 model. We can see in the original S3 model, the speed cannot go back to the original speed. But for the ES3 model, we can see the speed will return to the equilibrium state after disturbance. And the ES3 model offers stronger oscillation, obstruction, and damping. Okay, then we did a lot of stability analysis. Actually, we first analytically deliver the stability region, this curve and this curve. They are analytically delivered. We also did a lot of experiments. So we first fixed VF and KC, and also tau is the reaction time in the Cavorian. We fixed some of them, and we change sensitivity coefficient lambda. We change the flatness of the curve M. We change these two parameters, and we run the analysis to see if the traffic is in steady state or not. Okay, we can see almost the experiment are consistent with the theoretical bounds. And we can find that in high sensitivity coefficient, they're almost unstable. And in our analysis, so if we fix some parameters here, and we can only obtain the stable region here in this region, in the combination of flatness of the curve and static sensitivity analysis. We also use some global optimization algorithm for the calibration. I do not go to the very details of the algorithm, but I will show the results. So in this result, we can see the calibration, we use the speed for calibration, and we use the flow for validation here. Okay, we can see for the calibration, ES3 ranked, we compare ES3, IDM, and OVM. IDM and OVM are two typical used conforming models. Okay, now we compare the results, these three, and we can see ES3 ranked number 1 among 63% and ranked number 2 among 27% of this trajectory data. Okay, and for the validation, ES3 ranked number 1 over 70%. And also similar results for the average values. ES3 are the best among these three conforming models. Another one is the hybrid physics-based and data-driven model, physics-based and data-driven conforming model actually. So the existing conforming model have been developed from two perspectives, physics-based and data-driven, And for the physics-based model, we usually have this analytical form. A, the acceleration, the tau is the reaction time. Acceleration is related, delta x is the space headway. Delta v is the speed difference, and v is the speed of the foreign vehicle. They are related to these three terms. So these are very simple form. The advantage of this physics-based model is the parameters have physical meaning. Space headway, speed difference, and the speed of the foreign vehicle. They have physical meanings, and they can ensure reasonableness of the trajectory. But they also have some limitations. The limitation is they are constrained by limited parameters and mathematical formula, so they cannot describe complex driving behaviors. So looking at the data-driven model, it utilizes deep neural networks, reinforcement learning, imitation learning, and other advanced machine learning algorithms. So they don't need predefined mathematical form. And model training relies entirely on the observation on the data. So they can learn asymmetric behaviors, and the performance will increase with the quantity and the quality of the training data set. But because of this, they are affected by the quantity and the quality of the training data set, especially in the extreme traffic conditions with low data input. And also for the parameters, they lack interpretability. So another approach is to combine physics-based and data-driven model. In the literature, there are two approaches, result fusion and mechanism fusion. For the result fusion, it just estimate the data-driven model, estimate the physics-based model, and just use a weight to combine the result. This is the result fusion. But for the mechanism fusion, it integrates the loss function, integrates the alpha is a weight, into the neural network training. But in this mechanism fusion approach, this alpha is also predetermined, although the loss function is in the training process, but alpha should be, in this case, should be predetermined. So in our approach, we will adjust this alpha, this weight dynamically. So our perspective is also to propose a physics-based model and a hybrid physics-based and data-driven conforming model. So in the framework, we have the historical time steps. We input T steps for the historic data. And we need to predict the next L steps. If we use data-driven model, we can predict the next L steps all at once because it's data-driven. So we can predict the next L steps all at once. But if we look at the physics-based model, we can only predict the next one. And then based on the result of the next one, then we can predict the next one. Okay, iteratively. So this will be the physics-based model, predicts the next one, and then based on the result, predict the next one. Okay, so because of these two, we have two types of hybrid one. We will talk about the results of hybrid one and hybrid two later. For the hybrid one, it's from T to predict the T plus one, and from T plus one to predict T plus two. But for the hybrid two, we will predict the L steps all at once. Okay, based on this way, we will obtain the hybrid output. Okay, in this case, actually in the first beginning, I used IDM as the physics-based model, but in the revision process, the reviewer asked us to compare some more physics-based models. So I will, in our paper, revised paper, we will compare the IDM, S3, ES3, OVM, and other physics-based model. Okay, for the data-driven model, here, for the data-driven model, we use the multi-output Gaussian process regression as the data-driven model. It's the analytical part is simple. The basic idea is Gaussian process is a regression of this type. FL is the mean, and plus the epsilon is the error. And in this case, the epsilon is it follows a normal distribution with zero mean. It's an independent Gaussian process with white noise. So zero mean and the variance. Okay, then based on the Gaussian process, we can iteratively, also we have the posterior distribution, prior distribution. We can estimate the output. I do not go to very details of this MOGPR, but I want to highlight how we deal with the hybrid Ka-Fawley model architecture, because the physics model can be changed, the data-driven model can be changed to different models, but the framework is here. So in this framework, we have the data set. The data sets are divided into different data sets, small data sets. We have 5 different data sets. Calibration data set, training data set, validation, test data set, and reference data set. They are for different use. First, we use calibration data set. This will be used to calibrate the physics-based model. We will use test data set to test physics-based model. And for the data-driven model, we have validation data set, training data set, validation data set. They will be used to train a data-driven model. And the reference data set will be used in the hybrid model. Calibration data will be used in the hybrid model. And test data set also used in the hybrid model. Okay, look at this figure. First, we will have the calibration data set. So we will calibrate the physics-based model. And then we will obtain a calibrated physics-based model. And also for the data-driven model, we have training data set, we have validation data set. So we will train a data-driven model and obtain a trained data-driven model based on the calibrated physics-based model and the trained data-driven model. We will obtain the estimates from physics-based model and from estimate 2 from the data-driven model. And then for the hybrid model, we have reference data set, we have the hybrid algorithm. So the purpose of this hybrid algorithm is to obtain the weights. We have the estimates for the physics-based model, we have the estimates for the data-driven model, and we have the weights, so we can combine these using the weights to output the estimates. The hybrid algorithm is from the concept of the clustering. So for the input feature, here input feature include the speed, the space distance, space headway, and speed difference. Then we can calculate the similarity between the input data and each sample. So it's quite easy. But be careful when we do this, we need to do the normalization first because these three are in different scales. We need to make sure they are in the same scale. And for the auxiliary distance is used for the comparison. Okay, here for each input, we will have the results for the IDM. This is a physics-based model. We will obtain the results for the data-driven model. And in the existing fusion method, they just combine the results of the physics-based model, combine the results with the data-driven model, a physics-based model, data-driven model. But our proposed model is to incorporate the parameters, the weights into the training process and adjust them based on the input data. And this paper is now published in TRC. Okay, we will compare, as I said, we will have two hybrid mode. Hybrid 1 is to calibrate one by one, and hybrid 2 is to obtain the result all at once. We use NGSIM dataset for the test. Actually, in the revision, we also test different safeties, different datasets, and also test the transferability from different datasets. For example, calibrate using the NGSIM dataset and validate using the ZTD dataset. In our paper, we did this. Okay, in this experiment, we determined the prediction horizons. For example, how many steps should we predict is the best, and how many historical input is the best. We did this type of experiment. We find that when the historical input is 20 and prediction horizon is 7, it can obtain the smallest RMSE. We use direct plus SQP. This is a well-developed algorithm for the traffic flow calibration by Lee. Okay, we use this algorithm. This is open source. The code are open source, so we use it to calibrate the IDM. We can obtain the results parameters. Okay, then we compare the results for IDM, MOGPR, hybrid 1 and hybrid 2. We find that when the number of conforming pairs is very small, it's 10. Okay, we can see the larger of the RMSE, the worse of the performance. So we can see IDM, the RMSE is lower than the MOGPR, so IDM is better than MOGPR when the number of data, the input is small. But when we increase the number of data, increase the number of conforming pairs, we can see the data-driven model, MOPGR, outperforms the physics-based model. And we can also see the hybrid model, hybrid 1, hybrid 2, are all better than each of them. Okay, if we look at the weight, this figure, this is the weight of the data-driven model, the weight of the data-driven model. We can see from this time, we can see the weight of the data-driven model decrease. This is because if we look at the vehicle trajectories, the vehicles experience traffic congestion here. So in the congested period, we can see the weight of the data-driven model decrease in the congestion period. And in this congestion period, the vehicle experience congestion here. We can see the weight of the data-driven model decrease. Right. We also did this security analysis for the hybrid model. The scenario is this: a single vehicle travels through this road, and there is a standing vehicle in front, and we need to test the performance of the subject vehicle approach the leading vehicle. And we can see if the initial speed is 10 and initial distance headway is 15 meters, all the vehicle can stop safely. In this case, when the initial speed is 10, initial distance headway is 100 meters. Okay, this is unreasonable. You can see vehicle trajectory. It goes back. It is unreasonable. And if we look at this case, initial speed is 20, initial distance headway is 100 meters. The vehicle, even through this standing vehicle, 100 indicates the standing vehicle here. We can see this vehicle go through the standing vehicle and then go back. So this is data-driven model. It's unreasonable. Okay, the last one is the geometry-aware traffic flow model. If we search car following model in Google, we can see all the car following model, they assume vehicles are traveling on the straight line. All of these, they're on straight line. But if the road curve has horizontal curve, have the geometry, what should we do? In this case, actually for the road geometry, we have 1D, 2D, and 3D. Okay, I will be quick. 1D, 2D, 3D, and in our study, we can only handle 2D scenario, which means the roads are curved but without the height. In the 3D, we have variable space angles, but in the 2D, we only have plane angles. In our study, I can only handle 2D, and the student graduates, so I didn't continue the study. Okay, so in our, this is the traditional model, the isolation related to x1, x2, they are different variables. Okay, but in our model, we use geometry. We input geometry into the features, and we will train this using the parameters with these geometry properties. And this paper also published in TRC. Okay, look at the horizontal curve. We have 3 alignment types: straight line, transition curve, and circular curve. So connection mode, we have 3 types of connection mode. A is a straight line, B is a transition curve, C is a circular curve. So we have A to B, B to A, or B to C, C to B. We cannot have A to C. We cannot have straight line to circular curve. And we don't have circular curve to straight line to ensure gradual centrifugal force. And Euler space spiral is usually used for road design. Okay, then we have different car following scenario, internal car following. So A to A, B to B, C to C, and adjacent car following, A to B, B to A, B to C, C to B. Then we have this scenario loop connect different case. Next, we need to calculate the geometry aware car following feature. We may have different kinds of features. We have 7 different features, and we have some simple analytical derivations. Okay, now we will have different kinds of control mode because we have the scenario loop. We have 7 different scenarios. So if we use centralized control mode, then all 7 scenarios will be controlled using one model. But if we use decentralized control mode, then each scenario will have one model. We will compare the results. Okay, then we did some empirical analysis. We can see in this ZTD dataset, it had different alignment type, different attributes, the road geometry properties, and we can see straight line in this scenario. The straight line is 60%, and for the other scenarios, almost 40%. So this is a good example to show the geometry aware car following model. And we compare the results for the encoding, the decoding unit, we use LSTM, and for the input, we use these 5 different features. For the speed, it had 2 features. For the space headway, they had 2 different features. So, and also for the output, it had speed sequence. And for the attention module, we use the feature attention and also including feature importance and also temporal attention model. Okay, I just showed the results. If we use the M1 is the centralized control model and MX is the decentralized model, and we test the input step. When input step is 10 and output step is 5, the performance. And when the input step is 20 and the output step is 10, the performance. If we compare all the performance, we can find that our proposed geometry aware car following model is better than the normal car following model without geometric properties. We can also consider the importance in the task. We can see our proposed model, all other geometry aware features, they also have some importance related to the car following. So it is essential, it is necessary to incorporate the geometry features if the road is curved. Okay, now I will summarize my research. As you can see, my first study starts from the S3 model. And based on the S3 model, I continued another 7 studies. The study trajectory is from macro to micro model and then integrated macro to micro model, and also from deterministic model to the stochastic using log normal distribution, scale normal distribution, or copular. And also from model-driven to data-driven, and then hybrid model-driven and data-driven model, and also from straight line to the geometry-aware model. And last, looking ahead, I also want to do some research related macro, meso, and micro, because in our study, all the studies are focused on macro or micro without meso. And also consider merging and diverging traffic flows, and mixed autonomous and human-driven vehicles, and also consider large language model for generative data, and how to apply this type of traffic flow theory to traffic control and management. I think this is more meaningful for us. And that's all. Thank you.